What specific problem does MLE-bench aim to solve in the context of evaluating AI agents for machine learning engineering tasks?
MLE-bench aims to address the lack of comprehensive benchmarks that holistically measure the capabilities of AI agents in performing autonomous end-to-end machine learning engineering (MLE) tasks. It provides a structured offline competition environment consisting of 75 diverse Kaggle competitions that reflect real-world ML engineering challenges, allowing for a robust assessment of AI agents' performance against human-level benchmarks. By focusing on tasks that are both challenging and representative of contemporary ML work, MLE-bench enables the evaluation of model autonomy and the effectiveness of various agent frameworks. Additionally, it incorporates mechanisms to ensure fair competition, such as rules against direct solution recall and plagiarism detection, thereby promoting genuine engagement in ML engineering practices. Ultimately, MLE-bench seeks to reveal new insights into the prospects and limitations of autonomous ML engineering agents, facilitating a better understanding of their progress and potential impact.
How does the proposed MLE-bench method work? Illustrate the steps involved in creating the benchmark and evaluating agents' performance step by step.
The MLE-bench method involves several key steps in creating the benchmark and evaluating agents' performance. First, the benchmark is constructed by selecting 75 Kaggle competitions from a pool of 5,673 completed competitions, ensuring they are relevant to modern ML engineering and can be replicated for grading. Each competition is annotated for problem type and complexity, categorized as low, medium, or high, based on the estimated time an experienced ML engineer would need to produce a sensible solution. Next, the dataset for each competition is prepared, often involving new trained test splits to maintain comparability with human scores on the original competition leaderboards. For evaluation, agents submit their solutions, which are graded using locally implemented grading logic based on the competition's predefined metrics. The performance of agents is then assessed by calculating the percentage of attempts that receive medals, bronze and above, and comparing these results against the private leaderboard of each competition. Additionally, the method includes safeguards against rule breaking and plagiarism, ensuring that agents engage in genuine ML engineering practices.
Can you provide a simple illustrative example to explain how an agent would participate in a Kaggle competition within the MLE-bench framework?
In the MLE-bench framework, an agent participates in a Kaggle competition by first accessing a specific competition dataset and its associated description, which is sourced from Kaggle. The agent is required to produce a submission file containing predictions generated by a separate model, ensuring it does not directly write predictions based on its own knowledge. For instance, the agent might utilize the AID scaffold to guide its approach, iterating on its solution over a maximum of 24 hours, while leveraging a local validation server to check the validity of its submission. After generating the predictions, the agent submits the file, which is then graded using the competition's evaluation metrics, and its performance is compared against the private leaderboard to determine if it earns any medals. This process allows the agent to engage in ML engineering tasks while adhering to the rules set forth in the MLE-bench framework.
What are the theoretical or practical benefits of using MLE-bench compared to existing benchmarking methods in the evaluation of AI agents?
MLE-bench offers several theoretical and practical benefits over existing benchmarking methods for evaluating AI agents in machine learning engineering. Firstly, it consists of 75 carefully curated Kaggle competitions that reflect real-world ML engineering tasks, providing a robust measure of agent performance against human-level benchmarks. This diversity in tasks, including contemporary challenges with significant real-world implications, allows for a more comprehensive assessment of an agent's capabilities. Secondly, MLE-bench incorporates a structured evaluation framework that includes grading code and leaderboards, ensuring that agents are compared fairly against established metrics, which enhances the reliability of the results. Additionally, The benchmark's design allows for the exploration of various factors affecting agent performance, such as the number of attempts and available computational resources, which can yield insights into the limits and prospects of autonomous ML engineering agents. Overall, MLE-bench not only measures performance, but also facilitates a deeper understanding of the operational dynamics of AI agents in practical settings.
How is the performance of agents validated within MLE-bench, including the metrics used and the experimental setup?
The performance of agents within MLE-bench is validated through a structured experimental setup that includes the use of Kaggle competitions as benchmarks. Each agent's submission is evaluated against a private leaderboard, which is preferred over the public leaderboard to avoid overfitting. The primary metric for validation is the percentage of attempts that receive any medal, bronze and above, which reflects a challenging standard comparable to top human competitors. Additionally, agents are allowed to access a local validation server to check the validity of their submissions, although this server does not provide scores. The experimental setup involves running agents in a controlled environment with specific hardware configurations, allowing a maximum of 24 hours for each competition attempt, and utilizing a grading code that aligns with the competition's evaluation metrics.
What key results were reported in the paper regarding the effectiveness of AI agents on the MLE-bench, particularly in terms of their performance across different competitions?
The paper reports that the best-performing AI agent, O1 Preview with AID, achieved medals in an average of 16.9% of the 75 competitions in MLE-bench. Performance significantly improved when agents were allowed multiple attempts. For instance, O1 Preview's medal rate doubled from 16.9% with 1 attempt to 34.1% with 8 attempts. Additionally, GPT-4o scored 8.7% with 24 hours per competition, but improved to 11.8% when given 100 hours. The results indicated that while agents performed well on competitions solvable with established methods, they struggled with debugging and recovering from errors. Overall, the findings highlight the potential of AI agents in ML engineering tasks, while also revealing their limitations in certain areas.